Last time we kind of finished the discussion, but not really on counters. Then let me recap a bit what the idea behind the counters is. Then essentially, if we go beyond one addition, we should try not to propagate the carry except when it's really, really needed. Then instead of relying on carry propagate adders, we can use for intermediate calculations carry save adders, which are still preserving the value while not propagating the carry. Then instead of memorizing the number as one number, we memorize it as two numbers, and we do repeated accumulations. And this brought us to the idea of building a tree of such carry save adders. And we are discussing that you can apply population counters. Then if you have n inputs, each input has a weight of 1. In order to represent the maximum number of ones in those n inputs, you need log n bits. And for that reason, we call those n to log n counters. The bigger your counter, the stronger the compression and the shallower the compression tree. However, in theory, a counter, an n to log n counter, it's one stage, but in practice, when you implement it, it will be a lot of stages. Now, one of the idea which brought a different approach in this field relates to these generalized compressors, which are n to 2 counters or compressors. Now, if I have n dots, I cannot represent that sum on 2. It's not possible. On 2, I can represent values between 0 and 3. Then, in order to preserve the value, because this is basically what I want all the time, I want to do calculations which do make sense. Otherwise, you know, I can give up on that. I have to find a way to propagate carries between columns without increasing the critical path. And that's the idea behind those compressors. And as you see, they work in parallel. You should picture in your mind the matrix with dots. And I'm applying those compressors on different columns. I take, let's say, n dots in parallel, each of them, and then each such counter will generating two outputs, a sum and a carry. Now, this can count for at most 3 as value. What should I do with the rest? The rest I will propagate to my numbers as I will call them horizontal carries, because even though they go to the next positions, they are not increasing the critical path. And the reason of that is because I am doing the calculation in such a way that those carries contribute later on in the calculation. They propagate between columns, but they are not contributing to the critical path delay. Now, as you see in here, it's suggested that in order to preserve the value, which is n plus a number of carries which I may get in that position, I have to have 2 bits for the output and some carries for next positions, next, second to next, third to next, whatever. Which means that I have to solve such an equation. There are many solutions for that. This is an 11 to 12 counter. And I can try to solve, this is the condition, and this looks like a solution, and this looks like another solution. This may be interesting, but is not okay from the feasibility point of view. I don't like numbers which are not powers of 2 when I'm working in radix 2. If I work in radix 5, it's a different story. Then I can use such kind of, carries. What did I do with that thing? This is essentially a very nice slide. And this is explaining, maybe in a different way, the philosophy behind those counters. Then this is a 4 to 2 counter. This is interesting because it has an implementation which is faster than the implementation which relies on full headers. You will see that in a sec. Then essentially such a counter, it's assuming the 4 dots which are in the column and a carry from the previous position. Then the value which this counter is computing is between 0 and 5. And I can represent it as a sum, which is this, which can be 0 or 1, as a carry, which is that, which it can be 0 or 2, and as another carry, which I'm not really propagating here at the output, I'm propagating to my neighbor somewhere here in the middle of the calculation. Then all of them together give me between 0 and 5. Then I am sure that I'm conserving the value. Now, where is that implementation? Oops. I saw a slide with the implementation. I'm pretty sure I saw it. Maybe it's in the book. Then I'm pretty sure I saw that slide, but maybe it's on multiplication. Then the idea is that I can build this counter with 2 levels of full headers. Then conceptually speaking, I'm doing my reduction with 4 to 2 counters, but inside each counter, I will have some full headers. Then practically the compression will not be more effective, but I can also implement this counter in a different way. And I'm pretty sure I saw a slide on with that, but I don't remember where. Do you have the book? Okay, we'll look in the break. Don't worry now. Now, there is another problem when I do multi-operand addition. And the problem is when my matrix is not really rectangular. And this problem is coming from the sign. We know that the most significant bit is carrying sign information. Doesn't really matter how we do it, 1's complement or 2's complement, that sign information, it's also contributing to the value. If I'm doing sign magnitude calculations, the sign, it's a different story than the magnitude. But when I'm doing 2's complement, which we most of the time do, I have to do something with that sign in order to align and do calculations between numbers with the same kind of weight. Now, I can do 2 things. There are 2 approaches. One is to do sign extension. We discussed that, and I said, if I repeat the sign bit 1,000,000 of times, the value will remain the same. Then I can repeat the sign in order to make the matrix rectangular. Then, if my matrix was something like that, you will see in a sec why this is interesting. These are the sign bits. And what I can do, I can repeat them in order to align. And this sign bit should be in line with all the sign bits here. This is called sign extension. And it is essentially a repetition of this value. This is 0, all of them are 0. If this is 1, all of them are 1. You can easily check that this is true, and I hope nobody has a question about why this is true. If you do have a question, you will make me very unhappy today, which I don't want to be unhappy. Okay, now, there is another way to deal with that. And the other way to deal with that is to say, okay, you know, those guys which are here, they actually carry a negative weight. They are negative numbers. We remember that in 2's complement notation, in order to compute minus x, what we do is x bar plus 1, right? Then what I can do is assuming that this is the sign. Excuse me. That's okay. You are welcome. Why should I excuse you? You are still in time. Academic quarter. It's the second academic quarter. Yeah, this is something funny. In the Netherlands, you start with a break. Then when you start the class, you start with a break, 15 minutes. Why is that?
Because of the public transit.
But you can do it the other way around. To have a break after. Is that equivalent or not? Okay. Forget it. Then, I would like to do something in order to get that value one way or another. And I rely on this transformation, which means that now, if those are my sign bits, I replace all of them with complements, and then I have to do something with 3, because I have a 3, right? Or not? Now, how do I get rid of that? Did I say something wrong, or?
Well, what's 3? I don't see the 3.
I have a -3 actually, because I was a bit too optimistic. Then I have to compensate because my value, just doing that replacement, it's much too high. Then I have to get rid of a -1 for each position. Then -1 for each position will give me here a -3. Now, I don't like -3, it's again a negative number. But you know, -3, I can write it like a -4 plus 1. So far, so good. Which will give me here a 1. And because it's a -4, will give me here a -1. Here is no transport, it's 0. But this -4 will get into this position as a -1. Again, I don't like this -1. But it's simple. I'll write it like a -2 plus 1. Then I will get here a 1 and here a -1. And I repeat this story until the -1 will get out of my window. If I get a -1 here, I can drop it, because the value will be conserved. Now, those are equivalent. Which one should I do? Which one do you like? Then this is repeating the sign. This is doing a bit of a calculation. Then I am inverting those bits, and I have to extend here, put some constants in order to compensate for whatever I had here, which was too much.
I will take the sign extension because you don't have to do any calculations, and well, the sign extension is just putting some extra wires in the circuit. Repeating your.
Is that really true? No, it's an opinion. Okay. But you said I'm just repeating and I'm not doing extra calculations. Is that really true? What's your opinion?
We should go for the second one because we can put the ones like the next levels of the trees, so we can save some circuit.
Okay, you are both right. This is easier in the sense that I'm just repeating, but it will cost me extra hardware. Remember, this is now my matrix, which means that all those guys here, they have to take part of the calculation. Even though they are the same, I would have to put a full header here, a full header here. They will do the same calculation, but I have to put them there. Or I can do something else, which is a trick, or circuit trick. Put just one and broadcast the signal, but this will create another problem due to the large fan-out. Then, from one point of view, sign extension is brilliant. It's trivial as a principle. I don't have to do any thinking. I'm very safe on not making mistakes in this rewriting of things, but it will cost me extra hardware. The second solution is beautiful in the sense that I save hardware. I just need some inverters here, but there is a catch. You see, instead of 3, I have 4 columns. 4 rows, sorry, not columns. then this column is taller, which may have an implication on the depth of the reduction tree. If I am lucky and this extension in the column height is not changing the depth of the reduction tree, then I won. If I'm not lucky and this will move me on the boundary, you know, from one depth to another depth, then I'll get a reduction tree which is whatever plus 1, then this is not a winning solution because I will lose in the performance. So far so good? And I think you are not happy about computer arithmetic in general because I always say solution depends on, which in general, you know, we all like to deal with certainty. If A, I do B. In here, you need to do a lot of interpretation of stuff. Now, this is a kind of recap because we discussed about it. This is about how you do modular multi-operand addition. You apply the same techniques that you know from modular addition. Then what you do is, if you do multi-operand addition modulo 2 at power k, you just do it as it is normal. You apply full adders, and whatever is going out of your domain, you just drop it. You would have done the same for a modular adder, normal modular adder. If you do 2 at power k minus 1, what you would have done is to do end around carry. Then if there is a carry, you just inject it in the first position. And in a normal standard modulo 2 at power k minus 1 addition, this will result in one addition and then another addition in order to absorb the carry. In this case, we are lucky because in here, there is a missing dot. And then the end around carry will come directly in this place and there is no extra carry propagation. Then the property of the carry save addition still holds. And if I do the other one, which is slightly worse than the previous, which is 2 at power k plus 1, I will just have to place here an inverter on the critical path. Which means that even if I do modular addition, I can rely on that kind of, you know, carry save adders with the precaution of injecting carries which are going out of the boundary in the right positions and in the proper way. Now, if I'm not dealing with special moduli, then I have to play creative. And playing creative may be a bit complicated. And this is one idea on how to do it. And, you know, you start, this is a modulo 21 calculation. You don't struggle to do it directly in modulo 21. You do most of the calculation in a modulo that you like, okay, in a simple moduli. Then instead of doing modulo 21 calculations, you actually do in modulo 64 calculation. And then when you get the final result, you will force, you know, you will force your imagination and the final calculation will be modulo. There is no predefined solution for that. But this is a hint that whenever I have a modulo calculation which is not beautiful and not the simple moduli, I should try to make a detour. Then don't go brute force approach. Try to find a moduli which is okay, do calculations in that, and at the end of the day, when you are almost done, you do the modulo that you want to have. And I think with that, we are done with multi-operand addition. And the big thing that we have to remember is that multi-operand addition, then when I'm doing a chain of additions, the key answer is carry save addition. The second item which I should remember always is to deal in a proper way with the sign. No proper handling of the sign will give me wrong results. If I get wrong results in the exam, I don't pass it. which is bad. You have to see me again, which I think you don't like to have. Okay. Now we'll move towards the next operation, which is multiplication. Multiplication can be done via addition. And we also had some kind of work in how to speed up the multiplication by discussing that multi-operand addition. Okay. Let me switch to the other presentation. Then, when did I say we should discuss the second homework? Wednesday? You are not aware about the planning. You don't care about the planning. Then I can do whatever I want. Hmm?
In the schedule is today.
Sorry?
In the schedule is today.
It's today? Oh. Okay, we'll do it on Wednesday. No. We can do it also today, but I have to look for the solutions. Now, let us forget about the jokes. You can enjoy them. You know, jokes are very much cultural. And humor is not always universal. It took me some time to understand Dutch humor. Is there such a thing as Dutch humor? Hmm? Which is the closest humor that you may imagine close to Dutch? Hmm? Is it close to the British humor? Yeah? Hmm. You know, this is an important part of the culture. There are things that you have to understand about the society, and humor is one of them, and the body language is the other one. And, you know, Europeans can understand each other. People from Asia then can understand each other, but when you are far away, it's a bit difficult. Huh? And I cannot read the faces of my Chinese students when they are okay or not. It's difficult. Okay, now, you got your break, then we can focus on multiplication. Then multiplication, it's now a kind of different operation because I take two k-bit operands and I'm obtaining an operand which is a lot larger. It's 2 k-bit number. Why is that? Because by multiplication I'm actually increasing quite a lot the maximum value that I obtained, and it's between 0 and the product of those two. And in the primary school, this is the way you learn multiplication. This is the way we do it in computers as well. Then we take each bit of x, we multiply it with a, one at a time. We always keep into our mind the fact that the bit of x has a certain weight. Then 2 power 0, 1, 2, 3, whatever. And you get this kind of matrix. If this is an unsigned multiplication, your job is to add those numbers together and get this solution, and there is no other kind of headache. If you have sign, then you have some problems. Because if the sign is here, that's not a problem, because when you multiply this, it's in binary now. It can be even a or 0. Then you will just copy it. But when you multiply this with a, then this is a negative weight. And then you have to deal with that in a certain way. Then there are complications coming from that. Now, the simplest solution, remember on addition what we did? We said, let us try it serially. We do the same here also serially. Then I'm taking the bits of x one at a time from the least significant bit, and I'm adding them with the next one, and with the next one, and with the next one. Then essentially, this is an iterative process where if I start with my initial value P, this is my product, 0, I can compute the product of that, but I can also start with P as being another number, like C. Then I can compute now A times X plus C. Then in this way, I can absorb an addition in this multiplication. In many cases, this is of interest. In many formulas, when you write programs, you compute A times B plus C. Now, this is the recurrence of the multiplication. I'm starting from the top, and I'm arriving at the bottom, and each iteration, what I'm computing. I'm multiplying xj with A, which is a trivial calculation in my case because I'm doing binary calculation. If this would have been a decimal digit, then things would have been a bit more complicated. And I always have to keep in mind the position of this. And then after I do that, I make the addition with the previous value, and I make a shift in order to prepare for the next iteration. If I'm not making the shift, I'm not aligning right on the calculation. Now I can do the same from the bottom to the top. And this will give me that kind of recurrence. Both of them are bringing me the same result. Both of them allow me to compute AX plus C plus another operand. One is starting from the least significant bit of X. The other one is starting from the most significant bit of X. This is kind of strange because when we are talking about addition, I was saying, no, we cannot start from MSB because carries are traveling from SLB to MSB. How come that in this case it's okay? You are too active.
Yeah.
You have too much
It
adrenaline.
happens in morning.
Hmm?
During morning it happens. The rest of the day is late.
The rest of the day you are an early person.
Yeah.
You are like a rooster.
Rooster?
Yeah. You don't know, the rooster is waking up at 3 o'clock and it's making noise. Yes?
It's like 4 different numbers. The way you add them is like the same.
Sure. Then there is not about the propagation of the carry, it's about the order in which I process them. As long as I align them in a proper way, and I'm doing that with shifts to right or to left, it won't be any difference. Now, we usually prefer this one, and I won't ask you why, because you will not tell me. I know you are very shy, or you will tell me why the first one is better. Not you. Somebody else, you know.
I'm not sure. I'm just trying.
You know,
Just give me
you have to dare, right? Why would I prefer the first one? Yes.
In the second one, you have to shift the product to sum, so every time you have to wait before you can.
You have to do the same here, right?
But there you shift the input. Oh yeah, also. So, yeah.
You are right. You are in the right direction. In this case, I have to wait for the shift and then do the addition. And then prepare for the next iteration. Then the shift, it's part of my cycle. While in the first one, essentially, I do the addition and I will do the shift later on while I'm preparing for the next iteration. Then essentially, this one is slightly faster. And you have a 0.001 bonus point for the exam, right? Will that matter? You never know. We are rounding the grades, 0.5. In 20, they are happy, they don't have that. But this is not fair, because if a student in 20 will get 5.5, will pass the exam and you know the course, and if you guys get 5.5, you don't pass. Advantage them. But from the other point of view, we are not really communicating. Life is. Now here we have some examples, how you do binary multiplication. Then I start with, we'll go together through this algorithm, just for the sake of, following it together. Then, first, I start with P0 and 0, and then I compute x0 times a, which is just a repetition of a. I do the calculation, and I do the shift, right? And this is 2p1, and then I'm doing the shift. You see that I am kind of padding this number in order to preserve the value. Here, both of them are unsigned numbers. If I would have had to deal with signed numbers, I would have to sign extend. Then I'm at the next iteration. This is my previous accumulation. Now this is the new again because it's one result, shift. Now I add a 0, result, shift. I add another one, result, shift, and I'm done. And what you see is that because of the way I started the calculation and because of the shifts, my product is well aligned with the operands. Then the operands are, k bits are on the right side, starting from 0 to 48. And then my product is the same and is well aligned as well. Now there is something else that I observe. I observe that I am always using a 4-bit adder in this calculation because due to the shift, some of the bits in the result are leaving the calculation. They don't take part of. And this is another advantage of this approach, which you could not see in the previous slide and you could not, mention to my questions, but this is a fundamental advantage. Now, if I go for the other way around, then I start from the most significant bit of text. What you see is that I'm doing the same story, but the dimension of my adder, it's increasing. There is always a catch when you start from the most significant bit, because you have to keep things into the window. When you move from least significant to the most significant, there are things which are leaving the calculation. This is kind of obvious if you look at this matrix. If I'm ready with the calculation here, remember also when we are doing reduction, some of the bits in here are leaving the calculation. The same holds true here, and while this, in the worst case, in the last iteration, will require a 2k bit adder, even though one of the operands is narrower, it's only k bit, I have to propagate the addition, the carry from here until the end. And this is the biggest disadvantage of this approach. Now, long time ago, when you were not around, and I was a kid, which is really a long time ago, we could not really implement multipliers. And what we did, we were having like program multiplication. Then we had an adder, and the adder with the instruction, of the processor would do the algorithm that we are discussing at programming. Initially it was a real program. Then when you are programming, you are relying on an emulation library. Also today, in some cases, when you program things on a processor which has no floating point unit, you rely on an emulation library. Later on, what we did was we had more hardware, was easier to implement, and we wrote that in microcode. Have you ever heard about microcode? Okay, this is a kind of program which is hidden. It's not like embedded programming, which is also hidden. It's happened at a different level in the hierarchy of the processor. Then embedded programming It's hidden because there is no interface. You cannot really interact in a nice way with that software. In here, it's a software which is happening at another level of abstraction. Then this software is actually giving you the support for your instruction set. Now, in those times, you know, was very bad. Because you would arrive in, let's say, about 200 instructions in order to do a 32-bit multiplication. But those times are all gone. This is history. This is Pharaoh's time. Then when we got richer, what we did was to try to implement it in hardware. And for that, we need ingredients. Because it's a serial kind of approach, we need registers. We also need an adder, because this adder is our basic ingredient in the calculation. We need to have some interconnects, and we need to have some smartness to control the thing. Then I have a critical data path, but I also have a control path, a final state machine which is controlling this. This final state machine is essentially close to trivial. What is happening? I'm scanning the multiplier x from the least significant bit towards the most significant bit. And I use that bit to control this multiplexer. When this bit is 0, I will just pass a 0 to the adder. When this bit is 1, I'll just pass a to the adder. Then after the propagation through the multiplexer, this adder can do the trick, and then we'll copy the result of this adder plus the carry out into a double register where I keep the product. Then I can do the shift in order to prepare for the next iteration. Now, there is something which it's an animation which will take a long time. There is something which I already observed in this figure. And this something is that while I'm scanning X and shifting X out, X, you know, is getting narrower in this register. And the product is actually increasing. Then while X is leaving the place, P is getting into the place, which gives me the hint to share the register. Then I will start with X in the least significant part of the P register. And while I'm processing, you know, one is growing, the other one is decreasing. Eventually, when I'm done at the last iteration, X ceases to exist. And in P, I have the result of that. Simple, clean, and nice. The cycle time is determined by the time to shift, multiplex, do the addition, and store. This is basically the cycle time. With this scheme, I can just do unsigned work. If I want to do signed, I have to complicate the story. Okay? Okay, this is an animation. Which is exactly doing what I just told you. Then this one is leaving, this one is growing, and eventually we arrive with the result. You can play with it. You have the PDFs on Parhami's website. Now, this is what I just told you. The fact that I can overlap the registers, and I can also do, you know, while I'm doing the store, I am doing the shift. Then somehow I am hiding the delay of the shift. Not completely, because a shift register and a normal register are a bit different. There is, I mean, in almost all the time, in order to get some advantage, I have to pay a price. Now, if I do it the other way around, then I am now processing X from the most significant bit, The principle is the same, and I will need, the difference is that I will need now a 2k bit adder. Then from the hardware point of view, this is not a good solution. I should drop it. Now the question is, what do I do when I deal with signed numbers? Whenever a is, one of them is signed, and this is a, I don't have any problem, because x, it's always positive, and I am treating the multiplication as it would have been, you know, normal unsigned multiplication with one difference. When I am doing stuff here, you know, I'm just sign extending. Then, in order to get the right result, because this is negative, and I am doing a shift, I have to sign extend. Otherwise, I lose the value. If I don't sign extend here, I'll get a 0, and suddenly my result will be a positive number, which is wrong. But unfortunately, life is not that friendly with us. In order to have a normal multiplier, you should be able to deal with all situations. All of them should be some numbers. And now, what is the difference between processing normal bits and the sign bit? Remember, the sign bit has a negative weight. Then I start processing x from the least significant bit. And before I arrive to the most significant bit, there is no difference. I'm just doing shift, add, I'm sign extending things. And then in the last iteration, what I have to do is I have to keep in mind the fact that that one has a negative weight. Then the one in the x on the most significant position is carrying a negative weight. Which means that instead of doing the addition of the next partial product, I will have to do a subtraction. Now, is that bad? Is that difficult? Will that create me a lot of headaches? It should not, because remember, two's complement calculations are making addition and subtraction very much the same. Then what I have to do, I just have to compute the two's complement of this guy, of that a, then I have to compute minus a, which is a bar plus 1. And this gives me this scheme, which is very much the same as the previous one. It's still with the possibility to overlap the registers. It is still possible to add things, to add a, to add 0, but also it's possible to add minus a. How am I getting that? I am kind of creating a bit of a complication here. Then my max should be able to provide a 0, an a, or a minus a. Now I am controlling the adder with a carry in, which will be 0 always except in the last cycle, because in the last cycle I have to do a subtraction. And that carry in, which is in the last cycle, will also tell me that here I have to do an inversion. And I have a max, which is a kind of non-standard max. When the bit in the multiplier is 0, we'll tell this max to provide a 0 at the output. Then I have an enable. Then when the bit in the multiplier is 0, this will produce a 0. When the bit in the multiplier is 1, this will produce an A. When I am in the last cycle, this will produce a minus A, and the hot carry will be absorbed here. then essentially I have the same hardware, I have the same kind of cycle time, because in here, I'm complicating this a bit, but probably it's not that relevant, and I can deal with signed numbers as they were unsigned. And then you can get a break, which I know you are waiting for.